Okay, let's get started. All right, today we're going to talk about more spectroscopy and spectrometry. Again, the resources, not only do we have Wade, this is from the Prentice Hall presentation by Joe Blackburn, but the big resource for to practice is the Silverstein book, which is really fabulous. They have a lot of information there. Looking at the National Institute of Advanced Industrial Science and Technology. This is a Japanese site, and you'll see that a lot of the spectra I've obtained is from this site, so I want to give them a lot of credit for that. I use Wikipedia for some of the theory, and the UCLA website has a lot of practice problems, okay? And then more theory and Gilbert Martin. But both 3, 4, and 6 are excellent resources for you. I think it's really important that that you use it. Okay, so let's go on to here's my arrow. The next slide. Okay, there we go. All right, so with NMR, you can use a lot of different nuclei. We talk a lot about proton today. We'll be talking about carbon-13 today. We do N15, so if you like NMR and you want to do peptide and protein structure, we'll be doing a lot of N15. We also use fluorine-19 and phosphorus-31. This is really useful if you like to do basically your nucleotides, and you're looking at RNA and DNA. Okay? So what's interesting is we always talk about electrons having a spin. But there's also this thing called nuclear spin. And any nucleus that has an odd atomic number or an odd mass number has a nuclear spin. Okay? And so what that means is kind of like a top, and it generates a magnetic field. So when we look at it, here's my spinning proton. We'll be focusing on the proton first. As it's spinning, it generates a current. When it generates a current, you have directionality to it. So in a sense, the way I like to describe it, it's like a bar magnet. You have north and south. Okay? So when we look at that, if you place a magnet into a magnetic field, okay, then what's going to happen is all your magnets are going to align with the magnetic field. They're going to either be with the magnetic field or against the magnetic field, but you're not going to have them in this direction. Okay? If they're against the magnetic field, north and north, it's a higher energy, less stable orientation. Lower energy is with the magnetic field because the north and south are aligned, and north and south are aligned. So what happens is when we do NMR, what we're looking at is we're exposing our solution with all these protons to a magnetic field. And they are going to line up with the external field or against the external field. Okay? So remember, when you're lining with the external field, it's your alpha state, lower energy. Against the external field, it's the beta state. Okay, it's a higher energy. So when I irradiate it, okay, a photon, I can excite my proton in the alpha state, and it jumps up to the beta state. That's an absorption. And so what happens is that when we do NMR initially, the continuous wave, I'll discuss that, we're looking at what frequencies knew that my protons absorb energy to go from the alpha state to the beta state. Now, as you know, when it does absorb actually this photon, it is in an excited state. And over time, it's going to actually relax, and it's going to emit that same amount of energy. So we can get an emission spectra as well from my proton NMR. Okay, so when originally NMR was developed, it was actually developed by physics. Some physicists, and what happened was they were expecting just to see a single peak, and suddenly they found out they had numerous peaks. And so it didn't satisfy the criteria they needed for the experiment. Got handed over to the chemist, and the chemist saw it and said, oh, we can determine the environment around these different protons because we see these differences. So I have basically a strong magnet, and I have my probe, has its sample, okay? And what happens is I start irradiating it, okay? And then I detect where I get absorption. And that's the classic continuous wave instrument. So like we were talking about with the IR and the monochromometer, you're just going to go through and sweep through all of your radio frequencies and then see where you get your absorption. Okay, that's a continuous wave instrument. It does take time. Sensitivity is not that great. Okay, that's a very classical NMR. Then, I apologize a little bit about, I'll read these out to you because it's a little blurry. Now what we use is we use FT NMR, again, Fourier transform. What you do is you have your sample, it's in your magnetic field, and you give it a radio frequency pulse. And what you do is when we pulse it, you knock down all your protons, so the magnets are now basically going to precess. You pulse it, and then as they precess, they're going to be emitting, since they're all excited, they emit the radio frequencies in order to relax and go back into equilibrium in alignment with my magnetic field. So as it's emitting all those radio frequencies, it's going to decay. This is called a free induction decay. So we pulse it and we give it time just to decay until it reaches zero in equilibrium. This is going to be in the time scale. You can see again that beat kind of structure that we saw for FTIR. You do a Fourier transform so you can see all the frequencies that were associated with this FID, the free induction decay. Okay, so all the again, this is what happened when they were first developing NMR. They were expecting that all the protons would absorb at the same amount of energy. But they're surrounded by electrons, and that's the difference. The electrons actually form a shield around the external shield. And so how much those circulating electrons create that oppose the magnetic field gives you an idea about the environment those protons are in. Okay? So here, let's say I'm at basically 70,000 Gauss. I have my magnetic field. I have an alignment. I pulse it. Okay? It absorbs it. Okay? Now, if the shielded proton feels less, if I have, okay, if it's naked, it sees the full strength. If it's shielded, I have electrons that are protecting it from my magnetic field, then it feels less than the 70,000 Gauss. So what that means then is that when I apply my field, I have to apply something slightly stronger to compensate for the shielding. And that's what we see. So when we talk about NMR, you're going to hear us talk about shielding and de-shielding. Shielding means it's going to have to be a stronger field applied. De-shielding means I have less of an effective field, and so it looks more like a naked proton. Okay, so let's take a look at the protons in a molecule. So they're shielded in different amounts. Let's talk about this one. This proton, remember we were talking about polar bonds? Well, this oxygen is very electronegative, so it's pulling those electrons away from this proton. So it's less shielded. There's not a lot of electron density, so it's going to absorb at a lower field because they don't need to compensate as much. These protons are adjacent to a carbon. Carbons have more electrons around it than a proton does. And it's not electronegative like oxygen is, much less. So when it's exposed to my magnetic field in NMR, it's going to absorb at a higher field because it's more shielded. I need to compensate for it more. Okay? So when we look at the signals, the thing about NMR, which is so delightful, okay, is there's so much information in there. One, the number of signals in a proton NMR tells you the number of different types of protons that are present. Not the number of protons present, but the different types. The location tells you how shielded or de-shielded it is, which gives you a good idea of the types of environment around it. The intensity, essentially what we're looking at is the area under the curve. The intensity of the signal shows you the number of protons of that type. It's not the absolute number, they're all relative. Okay, so, but it tells you, oh, this signal has 3 times more protons than that signal. Okay, and the splitting shows you the number of protons on the neighboring atom. Okay, so you know how many different protons you have, you know type of environment they're in, you know how many of each of those types of protons you have, and the splitting tells you the neighbors. So you know where they're located. Who are my neighbors? Okay, so let's take a very simple graph of methanol. Okay, we said this was more shielded because it's on a carbon. So it's going to be what we call upfield. This is de-shielded, so it's downfield. Okay, so this is upfield, increasing magnetic strength, downfield. Okay, now what is that? We need a reference point, so that's my reference point. Okay, so I'll tell you what it is. That peak is tetramethylsilane, TMS. You don't need a lot, because look at all the protons in here. You need bare minimum drop. Okay, the only reason you put it is because silicon is less electronegative than carbon. These protons are going to be very shielded. So what we've done is we've defined TMS to be equal to 0. Okay, if we do that, then basically my organic protons absorb downfield to the left of that TMS signal. So this is very typical. All you're going to see is mostly your protons here. Is it possible you can see anything to the right of TMS? If you do, and it is possible, okay, I've seen something at negative 0.2 ppm, really, really, very beautiful. That gives you a very strong indication of what kind of environment that proton is in. It's more shielded than even TMS. Okay, so where are these signals? That is really good, like I mentioned with the IR, I think is really important for you to know, memorize basically, some of the chemical shifts. And I'll tell you which ones that you should know. And the reason I'm going to tell you which ones you should know is this. If you know on a methane, a methyl group should be below 1. So methane here is 0.2. Then if you see something higher, then you know that there's some electronegative atom on that carbon that's pulling the electrons away from the hydrogens and de-shielding it. So you can see that 1 chlorine moves it from 0.2 to 3. 2 chlorines on that same carbon has a huge effect still. It went up another 2.3, so that's 5.3. 3 chlorines, excuse me, I say carbons. 3 chlorines on here moves that chemical shift up. It's downfield at 7.2 ppm. Okay, so all of those add up and cause additional decreases in electron shielding, and so it shifts it far downfield. Okay, so what are typical values? If you know in an alkane, a typical methyl group is about 0.9. Okay, an alkyl group, but just looking at a methylene, you're looking at 1.3 ppm. An alkane, with it's just a methine, 1.4 ppm. So, here's the thing. See this methyl group here? That's a methyl group. You would expect it to be 0.9, but it's not. It's at 2.1. And why is that? Because it's right adjacent to an electron withdrawing group, the carbonyl. Okay? Alkynes is 2.5. And why is that? It turns out with this electron density, it shields this proton. And that's why it's only at 2.5. Halogens, we were seeing, chlorine, how the effects of chlorine, the effects of oxygen, okay? You're going to see these between 3 and 4. And as you continue to add more, it's going to continue to become more down shield. Alkene hydrogens, a vinyl hydrogen here, is 5 to 6. So you can see I went from sp3, 0.9, sp2 to 5.6. sp, because of the electron current there, went the other way. It went to 2.5. Okay? So, when you see a vinyl methyl group, an allylic proton, it's at 1.7. So we know that when I had a proton here, the current from this double bond deshields it, so it's 5.6. So I've got my carbon, and this is going to be deshielding group, and that's why it's 1.7 instead of 0.9. Aromatics, 7.2. A methyl group on an aromatic, instead of 0.9, because of the deshielding aspects from my phenyl group, 2.3. Okay? My aldehyde hydrogens, 9 to 10. Very distinct in that region. Particularly your carboxylic acid proton, almost bare, 10 to 12. Alcohols, it's variable, 2 to 5. Aromatic alcohols like phenols, 4 to 7. And then amines are 1.5 to 4. If you get amides, you're going to find them a little higher up. Amides would be probably between 6 and 7 or so. Okay, so what happens with my aromatic proton? Because I have the circulation of electrons in this direction, I end up getting a field that reinforces, see the directionality? It's in the same direction as B naught. So what happens is I don't need to have a strong magnetic field in order for this proton to be affected by it. So you're deshielding because of your aromaticity and the circulation of your ring current. You are deshielding that proton naturally. And that's why you're way up at between 7 and 8. For vinyl protons, same thing. Because of the motion of your electrons in here, that too deshields your protons. That's why we saw this between 5 and 6 for my parts per million, my chemical shift. What's different here is when we look at my triple bond, the acetylenylic protons, right? This is in the same direction, but see where my proton is? That's when it's going countercurrent, right there. It's going countercurrent where my proton is. So it's being shielded, and that's why my chemical shift moves towards the shielded upfield, towards 2.5 parts per million. Okay? Electronegative atoms, okay, so we've got your double bond from your aldehyde. That's going to deshield your proton. You have two, basically, properties affecting it. You've got the deshielding because of the motions of your double bond, plus you've got a very electronegative group pulling on the electrons off that proton. And that deshields it and moves it downfield all the way to 9 to 10. Okay? You're going to see the same thing for your carboxylic acid, and that moves down even further because you're on oxygen. Okay, so OH and NH signals. Hydrogen bonding, so you're going to see 3.5 approximately for a nitrogen-hydrogen, and about 4.5 for oxygen to hydrogen. Because it's exchanging with your solvent, a lot of times it broadens your peak. Sometimes you might not see it at all. Okay, so here, this looks to me like a methyl group. Okay, it should have been 0.9. Got shifted up to about 2.1, so it went downfield here. And so that means that I'm next to a very electronegative group. This is a typical area for a methyl to be adjacent to a carbonyl group, right here, right? But here, this is offset at 2.5, so I take 9.3 plus 2.5, that means it's about 11.8, okay? That's so far downfield, that's definitely a carboxylic acid. It's unusual because it's so nice and sharp. This is a very dry sample. At 0, we set it to basically TMS that's in there. We set that to be 0. Okay? So when you look at your chemical shifts, our reference point is 0. So that's what we set it to because it's all relative. Okay, parts per million. So once we set that to 0, then we can give a chemical shift to everything else. Okay? TMS is at 0. 1, 2, 3 different types, 3 different kinds of protons. Okay, and then we'll talk about splitting next. So I have A, look how intense this signal is. I have B, okay, and I have C. Notice this is smaller than B because they only have 2 protons, not 3. Okay, so this one is a little bit higher in chemical shift value, more downfield, okay, than what you expect for a methyl group, okay, and you expect it to be around here. It gets moved downfield because it's next to on a carbon. These hydrogens are on carbon next to a carbon next to oxygen. So the influence just being, if these hydrogens were on the oxygen, would be over here. Hydrogens on a carbon on the oxygen would be higher, but then a hydrogen on a carbon to oxygen, that influence is farther away. You're only going to shift it downfield about basically 0.6 ppm. So the effects, when you're looking at long range effects, by the time you get 4 bonds away to 5 bonds away, pretty much it's negligible. Okay, so this is 1, 2, 3 bonds away, and you can still see how strong of an effect this has. At the 2.25, this is right next to a carbonyl. Not surprising. Usually in this range, acetone is right, 2.4. Okay. Then at the 3.35 or so, look at, I'm between 2 carbonyls. 1 carbonyl right here. 2 carbonyls, another shift, about another 1 part per million chemical shift. Okay, so you can see the effects, the additive effects of electron withdrawing groups. The intensity. So what we do is see this line here. Okay, this is called integration. And we're looking at the area under the curve. Okay, and so if you look at the trace and you say, okay, so from here to here, that's about 2 spaces. Well, if I look from here to here, that's 1, 2, 3, 4, about 6 spaces, right? This starts just above. So this is 2 to 6. So the ratio between these hydrogens and these hydrogens is 3 to 1. Okay? So it doesn't mean I have only 3 protons and 1 proton. All it tells you is whatever number of protons are in here, I have 3 times as many of these as I do those. So that's what integration tells you. Okay? And if we're looking at MTBE, right, methyl tert butyl ether, you can see I have 9 here to 3, so that's 3 to 1. So when you know your molecular formula, then you'll know that you have 9 protons and 3 protons. Right now you only know the ratio. Where do you get the molecular formula? Remember we were talking about mass spec? That's going to help us because we'll know our molecular ion mass. And so we can start figuring it out from there. Okay, splitting. Splitting, what happens is that you're going to have adjacent carbons with protons, and they're going to have a magnetic field that will affect the proton of interest. Okay, so let's see how that works. And when it has an effect on it, that means it'll also be shifting it slightly downfield, slightly upfield, and that's why your peaks get split. And it can start getting pretty complex, and it's a lot of fun. It's a lot of fun. Let's do something straightforward first. So when we look at something that's non-equivalent, okay, if it's exactly the same, if they're equivalent protons, then it's going to be the same signal. But if they're non-equivalent, they can affect each other. So let's take a look at this one. 1, 1, 2, 1, 1, 2, tribromoethane. Okay, these protons are equivalent. That proton is just one, but these two, A and B, are different. Okay, because B is on a carbon with only one bromine, and this is further removed, that's why you see the chemical shift at 4.1. This hydrogen is on a carbon that has two bromines, so it's going to be shifted even further, and that's why you see it at 5.7 ppm. Now, these protons have one neighbor, so that neighbor splits it slightly upfield and downfield. This one has two neighbors, so these two can affect it. So now I have a shift downfield, upfield, but now I have 3 peaks when I have two neighbors. I have 2 peaks when I have one neighbor. So what you're doing is that every time you have a neighbor, the splitting is going to be caused by n+1. And when we talk about the neighbors, we mean equivalent, right? So if I have 3 neighboring protons and they're all the same, like I have a methyl group, then I'll see a quartet. It'll have 4 peaks in the splitting pattern. Okay? So what happened? These guys see the magnetic spin on HA, and it can either reinforce the field or it can oppose the field. It opposes, takes your peak, shifts it downfield, reinforces, shifts it upfield. So the actual chemical shift of B is right here, but it gets split because of the influence of A. Let's take a look at A. Now if I take a look at A, here's a chemical shift of A. Now if B, they both oppose the field, then it goes downfield. If it's B and both reinforce the field, then it goes, upfield, and it goes downfield. What's interesting is one could be opposing and one could be reinforcing. These are equivalent, and so the influence there actually keeps it right here, right in the center. Okay, so opposing the field goes upfield, reinforcing the field it goes downfield, and that's how we get our shifts. Okay, so what happens is this. It's called the n+1 rule. If I have n equivalent protons, then I get n+1 peaks. And you follow Pascal's triangle. So what we see is that if you look at the heights, and I'm going to go back, all right? For a doublet, it's 1, 1, same height. For a triplet, it was 1, 2, 1. So this is twice the height of that. If I had a triplet or a quartet, it'd be 1, 3, 3, 1. So it'll follow Pascal's triangle when you look at the area ratios. So when I look at equivalent protons, since they're identical to each other, they don't split each other. It's only if they are not equivalent. Okay, protons to the same carbon will split each other. Okay, on adjacent carbons, they're going to split each other. Okay, they're going to couple. And if they're farther than 4 bonds, they don't influence each other at all. Okay, so when they're splitting each other, that's called magnetic coupling. Okay, so let's take a look at this. Oh, look at ethylbenzene. Well, I think you've seen this guy before. All right, ethylbenzene, I have an ethyl group. Okay, and if you look at this carbon, this hydrogen to carbon's 1 bond, 2 bond, 3 bond, 4 bonds. So you're not going to see influence. You're going to see just 1, 2, 3. So this hydrogen to carbon, hydrogen, that's 1, 2, 3. That's a J3 coupling. Okay, so see this? 1.2. Should be at 0.9. So it's influenced, but not significantly. It is, you're thinking I have an electron withdrawing group, but it's not directly attached to my methyl group. What else do I know? This has 3 protons compared to this group. So 3, 2, and then 5 protons. Okay? So you know that we're probably looking at methyl groups here. We're probably looking at methylene, the CH2 groups here. Okay? And then what about this? Well, 5, it looks pretty messy, but you're in an aromatic range, so you're looking at a benzene ring most likely. Okay? What else can you tell? So we know this has been shifted. Look at, if this is CH2, and we know CH2 normally should be in this region, remember that table we showed you earlier? Now look at it, it's way up here at 2.6, right? So what does that mean? Something that's very electronegative or something that's very de-shielding is attached to that CH2 group. And there's another thing you know. So we'll go through the CH2 group, okay? So we know something's electron withdrawing. So I'm going to, instead of me telling you all at once, I'm going to break it down. We did the integration, so you know the number of protons in each group. We're doing the chemical shift, so you know the environment. So, basically, electronegative, de-shielded, de-shielded. This is your aromatic range. Okay? 7 to 8. That's aromatics. So, you see this? You go, oh, I most likely have an aromatic. We talked about your integration, C5, H5, 5 hydrogens. Okay, that means, oh, it looks like a monosubstituted aromatic. Okay, now let's take a look at the splitting. So, we know our integration, methyl, methylene, monosubstituted aromatic, ranges. This is de-shielded, even more de-shielded. Aromatic, we know that's de-shielding, so this is probably attached to the aromatic. That's further away because it wasn't affected, the chemical shift wasn't affected as much as the CH2. And then we say, oh, what about the splitting? See this? This is a CH3. It has 3 peaks, which means its neighbor has 2 protons. So this CH3 group must be attached to a CH2. You say, oh, what about this guy? Quartet, 1331. This is a CH2, look at the integration, but what is it attached to? It's got to be attached to a CH3 because I have a quartet. That means my neighbor has to have 3 protons. So this looks like an ethyl group, CH2, CH3. This is split by the CH2, that's split by the CH3. Now, if I have a CH2, CH3 group, then the question is, what else is attached to this, but it can't have protons on it? The only thing that could be attached to this that still makes sense for this is my aromatic ring. So, I have 5 protons. My CH2 is attached right here, so this hydrogen is too far away to influence, and that's why I only see a quartet, because it's just a CH3 that's splitting it. That is just so beautiful, right? So let's take a look at this one. All right. See this? 1.1.2. Okay. Look at that. Double it, right? 6 protons. What do you think it is? Exactly. 2 CH3 groups attached to a CH group. That's why it's a doublet, because the neighbor has to have only 1 proton. This one is a singlet. That CH3 group is all by itself. It's attached to something. I don't know what, but it doesn't have any protons on it, so that's why it's a singlet. Now look at this. 1, 2, 3, 4, 5, 6, 7. That beautiful 7, which means it must have 6 neighbors. So, this group that has an integration of 1, says a CH, must be attached to 2 CH3 groups. That's an isopropyl group right there. This one and this one, isopropyl. Look it. And this one is just a methyl group because I have a CH3, no neighbors that have protons on it. So now we have to think, what kind of neighbor will they have if it doesn't have any protons on it? So see how this has been de-shielded just a little bit? About 0.2. Look at this one. This is at 2.1. that methyl group should have been at 0.9. What do we know? Normally, a methyl group that's attached to a carbonyl is going to be right around 2.1 to 2.4, like an acetone. So here, maybe there's a carbonyl somewhere. So this had a methyl group attached to the carbonyl, and then the carbonyl was attached to the CH. That would explain why my CH group is so deshielded, and the splitting only is representative of the two methyl groups next to it, not by the other side of the attachment. Singlet, this is going to be a septuplet because of these 6. This 3 sees 1, so my methyl groups are going to see a doublet. Because it's next to a carbonyl, we're thinking 2.1. This, instead of methyl group at 2.1, it's going to be even further downfield, because remember, methine is already at 1.4 we start before we start deshielding it. These guys are farther removed, so 1, 2, so they're 2 to 3 bonds away, so you're not going to see a significant of a deshielding shift. Coupling constants. If you look at the distance between the peaks of a multiplet, they're measured in hertz, not dependent on the strength of the external field. They are called coupling constants, and it gives you an idea of the type of coupling. An average coupling constant, okay, when we're talking about basically our alkyl groups, these are all about 7 hertz, okay? That's what you would expect. But the values will be different if we have alkenes and we're looking at cis and trans and geminal hydrogens. Okay? So, what are the coupling constants? Free rotation. If I have 2 protons that are cis to each other, that coupling constant is 10 hertz. Trans, it's 15 hertz. If they're geminal, it's very tight, only 2 hertz. They don't affect each other too much. When you look at your coupling constants in your aromatic, if they're ortho, adjacent to each other, it's 8 hertz, but the meta have very little effect on each other, it's 2 hertz. And then basically, if I look at my allylic protons, that's going to be about a 6 hertz coupling. Okay, so you can get complex splitting, because now look at, these are geminal, that's 2 hertz apart. These are cis, this would be 10 hertz apart, right? And isn't this like 12 hertz apart or larger? Oh, 11 and 17. So let's take a look. Let's see, I said 12, 15, 10 and 15. Okay, 11 and 17 for styrene. Let's take a look. So, when we look at the splitting tree, this proton, okay, so let's take a look at A. A is split by C and by B. So we're not going to get, since these are not equivalent, we don't get the n+1 rule. We separate them out. So you have a doublet and a doublet. So you get what we call a doublet of doublets. So if we look at A to C is 10 hertz. A to B is 15, or in this case for styrene, 11 and 17. So A split by B gives me 17 hertz. And then the effect of C gives it another 11 hertz. Okay, so we would measure this and we say, okay, that's 11 hertz. And then we would take the halfway point, or you can measure here to here and here to here, and that gives you your other coupling constant, which is 17 hertz. What about B? B sees 17 hertz right there. And then those peaks are split again by the 1.4 hertz to 2 hertz, right? So you get a doublet of doublets, but you can see the pattern's different. So what does this tell you? Whatever proton that this represents is going to be cis and trans to the other 2 protons. Whatever proton we're looking at here has to be geminal to one and trans to the other. Okay, so this has to be B because it's geminal to one, trans to the other. So if we were looking at C, then I would see basically 11 hertz and then the 1.4 hertz. So you see this, and 2. So you're going to have this, but they'll be closer together, and the difference between the centers will be 11 hertz apart. And that would be the splitting you would see for HC. So, here. See this? If you expand it, look at that. Alright? That's going to be A. It's cis and it's trans. Here, for B, you can see these two small ones because it's geminal. And you can see the large distance apart. That's because it's trans. C, two small ones because it's geminal. And the distance between these two is smaller because it's cis.